Lecture number 3 for fluid mechanics. Let's continue from where we left. We are still looking at static fluids, and from static fluids there are about 4 things that we know up to date. The first thing that we know is a static fluid can have no shearing force acting on it. So which means the static fluid, there are no shearing force that are acting on the fluid. Then the next thing that we have talked about is any force that is acting between the fluid and the boundary must be acting at right angles with the boundary, as can be seen with these 2 diagrams that we have, that even if it's a curved surface that we have, the force that is going to act on the fluid, between the fluid and the boundary, is supposed to be at 90 degrees or perpendicular to the boundary, like what we've talked about. Then number 3 is the sum of forces in any direction is equal to 0, which means that the fluid is at rest and is in equilibrium. So the sum of forces should be equal to 0. So summation of forces equal to 0. Then summation of moments of the forces should be also equal to 0. So if we are looking at rotation of fluid that is in a rotational state, if the fluid is at rest, it's supposed to give us moments equal to 0. We also talked about pressure last time, and we defined what pressure is. We said pressure is force per unit area, or force, or also known as normal stress, if you remember what we talked about from lecture number 1. And the units that we use are still newtons per meter squared. Of course, in some other context, you can leave your answer in pascals or in bars. It's not a problem. But what we need to know is force per unit area gives us what is known as pressure. So from there are about 2 or 3 laws that we'll look at in this course or in this lecture today. The first one that we want to look at is Pascal's law. So Pascal's law is a proof that pressure acts equally in all directions. Pascal's law says that pressure acts equally in all directions. So if a fluid is at rest, which means if there is any pressure that is going to act in any direction, should be equal in any direction, whether it's in X, Y, or Z, the pressure is equal in this case. So here there's a proof that has been put to show that PS is equal to PY and is equal to PX. So you can go through these derivations that are here. I've never asked anyone to derive this law, but what we just need to do, we use this law a lot to know that in all direction pressure should be equal in this case. So for example, if we want to derive this Pascal's law, we have to find the force that is in the X direction, and we know that force is equal to pressure times area, deriving it from that definition of pressure, that pressure is equal to force per unit area. So we know that force will be equal to pressure times area. So when we play around with what we have in this diagram, we are going to get pressure, or force is equal to pressure times area, where our area is equal to change in X multiplied by change in Y. If you are looking at area, that is where this pressure is exerting, where this force is exerting, where the pressure has got this force. So which means it's at area A, B, F, E, which is A, B, F, E, this side. So which means PX is exerting pressure on this face, which is A, B, F, E. So from there what we need to do is to find this area. In this area we know that its area is equal to length times width, so it's equal to this multiplied by this side. So we are going to get our PX equal to delta Y multiplied by delta Z. In this case, this is just a typo that we have here, so it's supposed to be delta Y multiplied by delta Z. So here is equal to PX multiplied by delta Z by delta Y. So you can correct this part. Okay, so when you play around with these formulas and everything like that, we will notice that at the end of the day, the pressure at Y will be equal to pressure at S and will be equal to pressure at X. And from there, we'll be able to verify the law for Pascal, which says that pressure is equal in all directions. So you can go through these notes during your spare time, but good for you. I won't ask you how to derive all these formulas, but we'll use the law. So which means that Px is equal to Py is equal to Ps, and pressure at any point is the same in all directions. This is what is the Pascal's law, and it applies only to fluids at rest. So for example, if we've got, we want to find out how pressure is distributed vertically. So in this case, we have got a cylinder that we have and raised at a height of Z2 and also Z1. So Z2 is from the ground up to the upper top. Z1 is from down from the floor surface up to the bottom part of the cylinder that we have. And we want to find out how is pressure going to vary in a vertical orientation of this cylinder that we have. But before we go there, we have to find the force at point A, point 1, which is down here, and the force at point 2. So we know that these forces that we have, since the fluid is at rest, they are supposed to be equal. So summation of these forces is supposed to be equal to 0. So pressure at point 1 is equal to P1 multiplied by A. Force is equal to pressure times A. So which means here we are looking at point 1, it's equal to P1 multiplied by A. Pressure at point 2 is equal to P2 multiplied by A, point 2, which is up here. Then the force due to the gravity or due to the weight is mg, because there is a fluid inside here, so which means the force that we are going to get due to the gravity is mg, which is mass times density times volume, or mass density times volume multiplied by gravity. So here, if we say mass density is as good as writing as rho multiplied by v multiplied by g. And our volume, we can change volume to say volume is equal to area multiplied by height. And our height, the one that we want as our height, is the difference between Z2 and Z1. So we can write force due to the weight is equal to rho GA, Z2 minus Z1. So if we balance now our forces, we know that force, summation of forces is equal to 0 when a fluid is at rest. So in this case, P1A minus P2A minus this should be equal to 0. Then when you combine this force that you are going to get P2 minus P1 is equal to negative rho GA Z2 minus Z1. And this one is known as the hydrostatic pressure law or hydrostatic law or hydrostatic equation. We normally call it hydrostatic equation. So hydrostatic equation, you can write it as so from here we are going to get our hydrostatic equation. In the hydrostatic equation will be change in pressure is equal to negative rho GA multiplied by change in height, or which is Z2 minus Z1. So we call it hydrostatic equation. So now this hydrostatic equation, we might need also to check what we are going to get if this fluid or this container that we have has been put horizontally. So if it's horizontally, in this case, we are going to come up with what is known as Pascal law. We are going back to Pascal's law, because we know that when it's horizontal, the pressure in the horizontal direction is constant. So which means pressure at this point will be equal to pressure at this point. So pressure at L will be equal to pressure at R, and pressure at P will be equal to pressure at Q. So which means pressure at the two equal levels are the same for a continuous fluid. So for a continuous fluid, we are going to get equal pressures in horizontal direction. If we change density in this direction, let's say we've got mercury here and we've got water here, pressure at P and pressure at Q won't be the same. Similarly with L and R, if we've got different fluids, the pressure won't be the same. So what we need to put in mind is, if we've got continuous fluid, we are going to get pressures that are going to be equal at equal levels, or at the same level that we have. For example, this diagram that we have here, pressure at A is equal to pressure at B, C, D, E, F and G, despite the shape of the container that we have, despite the shape of the surrounding or the boundary that we have, on condition that we have got the same fluid. So in this case we've got water all over this place. But now pressure at H is not equal to pressure at L, because here we've got mercury and the other side we've got water. So we need to put in mind that the pressure is the same at all points on horizontal plane in a given fluid, regardless of the geometry, provided that the points are interconnected by the same fluid. So that's the catch here that we have, that it's supposed to be interconnected by the same fluid and supposed to be on a horizontal plane at the same points on the same horizontal plane that is bounded by the fluid, which is the same. Okay, so now if we put that container at an angle, we will know that at the end of the day, the governing equation that we are going to get will be change in pressure over change in distance is equal to negative rho g cos theta. So we need to factor in now this change in the angle or the gradient that we have. Okay, so this one will become our general hydrostatic equation. So to prove that, we can use the horizontal container. If we take this container to be horizontal and we want to use this same formula that we have, we'll notice that in this case our theta, if we continue going down, our theta will be 90 degrees. So if theta is 90 degrees, what it means that is cos theta in this case will be equal to 0. Cos 90 is equal to 0. So what it means now is change in pressure over change in distance will be equal to 0. So what does it mean? It means that dP is equal to 0 in this case, because change in S cannot be equal to 0. This is our change in S, cannot be equal to 0, the length. But in this case now, dP is the one that is equal to 0. So what it means now is P1 is equal to P2, which will take us back to Pascal's law, which states that pressure in the horizontal direction is the same provided the fluid is continuous. Okay, so now when you put this one in a vertical orientation, we know that if it's vertical orientation now, our theta is equal to 0 in this case. So if theta is equal to 0, cos theta from this equation will be equal to 1. So it will give us dP over ds is equal to negative rho g. So if you get negative rho g, this one will take us back to hydrostatic equation, where we can write P2 minus P1 over Z2 minus Z1 is equal to negative rho G A. Okay, so in this case now we are going to get P2 minus P1 is equal to negative rho G multiplied by Z2 Z1. But what we need to put in mind is we need to also factor in the area, like what we have in this equation. So P2 minus P1 is equal to negative rho G A Z2 minus Z1. So which means in our equation, even this general equation that we have, we need to include area here, multiplying by area, so that we can factor in the influence of the area in our equation. So correct this part, supposed to be P2 minus P1 is equal to negative rho G A Z2 minus Z1 to give us the hydrostatic equation. So from there, now we can apply this hydrostatic equation to also get issues to deal with pressure and the head, and also to calculate manometer and pressure problems. So from this equation that we have, dP over dz is equal to negative rho gz in this case, we will see that this is a differential equation. So if you have done your mathematics very well, you will know that this one is a differential equation, and as what we want to find is pressure. So from here, if we integrate both sides, we'll see that integration of dP in relationship to P will give us P. Then this dz, we take it the other side of the equation, we integrate in relationship to Z. We'll get this equation as P is equal to negative rho gz plus a constant. We know that when you're doing integration, we also have to include the constant. And this constant that we have in this case is the atmospheric pressure. atmospheric pressure. So this equation, when we include this h, which is the distance, and h, we can take h to be equal, or like z is equal to negative h. So when we replace z with negative h, we will get our equation as P is equal to rho gh plus the atmospheric pressure. Okay. So from this equation now, we are going to differentiate, to explain and have about 3 or 4 types of pressure that we are going to look at in this course. The first one is known as gauge pressure. So gauge pressure is defined as rho gh. So if we neglect atmospheric pressure in this equation, what we are going to get is known as the gauge pressure. Then from gauge pressure, we also have what is known as absolute pressure, which is rho gh plus the atmospheric pressure. So when we've got atmospheric pressure included in the equation, we will get what is known as absolute pressure. So you need to be conscious. Most of the time, when we are asking you to find the pressure of a given system that we have, normally we are asking for the gauge pressure, because atmospheric pressure is usually taken as datum. So if it's datum, so which means atmospheric pressure is usually taken to be equal to 0. So absolute pressure, if you're asked to calculate absolute pressure, you need to include atmospheric pressure. But however, most of the time the question that comes is they are always asking for gauge pressure. So gauge pressure, put in mind that is rho gh. And atmospheric pressure is usually a datum. So datum, it means that atmospheric pressure usually take it to be equal to 0. Then the next thing that we have also is also what is known as vacuum pressure. And vacuum pressure is any pressure that is below atmospheric pressure. Okay. So we can also define the vertical height, which is known as the head. So when you're talking about the head, I'm sure most of you have heard this term, the head. Like if you are going to buy a pump, most of the things that you are concerned about is this pump, how much head, what is the head that it can provide. So head is the vertical height that you are looking at. Okay. Sometimes we can quote the pressure in form of head. We've got what is known as the pressure head. So pressure head will be defined as rho gh divided by pressure. So pressure head will be defined as rho g divided by pressure. Pressure head is defined as rho g over pressure. Then that way we've got our pressure head. So from this example that we have here, we are given this pressure in head of water, and you know the density of water is 1000 kg per meter cubic. So you are supposed to find what is the pressure head from this situation. So from this situation, we know that pressure is equal to rho gh, make h the subject formula, then you get your pressure head from this equation. So this diagram simply summarizes everything that we're talking about in terms of pressure, the types of pressure that we have: absolute pressure, gauge pressure, vacuum pressure, atmospheric pressure. So like what we talked about, we say that atmospheric pressure is the datum or the boundary or the zero line that we have. So if it's the zero line, which means vacuum pressure will be below atmospheric pressure. Vacuum pressure below atmospheric pressure. Then gauge pressure and absolute pressure, they are above atmospheric pressure in this case. Okay. So let's conclude this class by just talking about the different types of manometers that we have and their limitations. Then the next thing that we'll be doing is solving and calculating problems. So the first thing that we have is known as the piezometer tube manometer. Piezometer tube manometer is the simplest manometer that we can have with an open tube. So which means this one works mainly with the gauge pressure. So which means we are measuring the gauge pressure that we have here. So pressure at A, for example, pressure at A will be equal to rho GH1. Rho GH1. So it just be equal to the pressure due to the column of the fluid H1. Then pressure at B will be equal to rho GH2 due to this column at H2. Okay. That will be the pressure that we are looking at. So just simply measure this height of the fluid that we have and multiply by the density of the fluid and gravity. So the problem that we have with the piezometer can only be used for liquids, and the pressure must be above atmospheric pressure, and liquid height must be convenient, not too small and not too large. Those are some of the inconveniences that we can get when you're using a piezometer tube. Then the next type of manometer that we have is the U-tube manometer. So with the U-tube manometer, that principle or the law of Pascal, Pascal's law, applies a lot in this part, because you know that Pascal's law tells us that the pressure in the horizontal direction is equal provided the fluid is continuous and static at the same horizontal level. So in this case, we've got a fluid in this U-tube. So what we need to do is to find where the pressure is going to be equal. So in this case, first we need to find where the fluid is continuous. So if you've got fluid B here, which is manometric fluid, usually it's mercury. So if you've got mercury here, for example, so where there is a boundary between the mercury and the fluid density of rho here, we will know that at point B and C, the fluid is the pressure is going to be the same, because we've got mercury here and we have got also mercury this side, and they are at the same horizontal point that we have. So pressure at B will be equal to pressure at C in this case. Then coming back to this simplest manometer that we have, the tube manometer, we'll divide our manometer to be in two. So we can divide it to be this side, the left hand side, and this other, the other side to be the right hand side. So for us now to solve this problem, we have to look at pressure at B. So pressure at B, anything above B will give us the pressure at B. So pressure at B will be equal to pressure at A, which is this one, plus the pressure of the height of the fluid above B. So which means this is the height that we have, H1. So mathematically we can write PB is equal to PA plus rho GH1. So this pressure due to the column H1, we know it's gauge pressure, which is rho GH1. Then we do the same thing again to the right hand side, which is now pressure at C is mainly due to pressure due to this column H2. Someone might ask that this one is open, why are we not putting atmospheric pressure? Atmospheric pressure, we say that it's our datum. So if its datum is solely equal to 0, you can include it, then it becomes absolute pressure that you're looking at. But in most of the cases, even if it's open here, we usually consider atmospheric pressure to be equal to 0 because it's our datum. So what we are going to get now at pressure at C will be equal to atmospheric pressure plus rho GH2. Since our atmospheric pressure is datum, we can just write it as PC is equal to rho GH2. And the rho that we have to look at is the rho due to the manometer. Okay. Then now from there, we have to equate P at B is equal to P at C. Then we find what we are looking at. For example, in this case, we are calculating A. Then we can find our area. So if we are dealing with fluids like gas, nothing changes per se, but the only challenge that will happen now is in this case is the manometric fluid will be far much greater than the fluid density. For example, gas in this case. Look at it. The density of mercury is 13,600, and you compare it to the density of air, which is about 1.23. Then in this case, we can say that the density of the manometric fluid is far greater than the density of the fluid that we are looking at, which is the gas. So at the end of the day, we can neglect rho GH1. So what will happen now is pressure at A will simply be equal to the manometric density multiplied by G multiplied by H2. Okay. Then the other type of U-tube that we have, even if we are dealing with inclined plane like this, let's say we've got a fluid in this pipe, then we've got it's at an inclined position that we have. What we need to do is to first identify the point where we've got continuous fluid, and at the same horizontal point. So pressure at C is equal to pressure at D in this case. Then we do the same thing that we did last time. Pressure at C is equal to pressure at D. So we isolate the left hand side and the right hand side. We look for all the pressure that is at C. So pressure at C, we've got pressure at A plus the pressure due to this column HA. So we are going to get PA plus rho GHA. Then pressure at D, we do the same thing. So in this case, we've got two different liquids that we have. We've got this liquid that comes up to this point, and we've got this liquid that comes from this point up to this point. So what we need to do is isolate them. So we are going to get pressure at D is equal to this column H, which is going to be rho manometric multiplied by G multiplied by H. This is the part. Then we've got now another column which is HB, this part. So we are going to say that this density that we are going to get is rho G HB. Instead of plus here, we're supposed to say minus. Oh, rho HB plus H. HB plus H to get this column that we have here. Okay, so then from there we equate PC is equal to PD. PC is equal to PD. Then we take the pressure due to C, which is rho PA plus rho GHA, should be equal to PD, which is this equation. PB plus rho G, open bracket, HB plus H, plus rho manometer GH. We equate the two. Then we find the pressure difference, which is PA, PB. We get this equation that we have. Okay. So what can we do now with some of the advances in the YouTube manometer? We look at a point whereby we've got a bigger diameter this side and a smaller diameter this side. And the same thing that applies. We have to look at the point where the pressure is going to be equal, and we solve our problem like what we did before. Pressure at this point should be equal to pressure at this point. Then from there, we can get our equation as P1 minus P2 is equal to rho G Z2 plus Z2, open bracket, D over capital letter D squared. Okay. Then next step is to look at inclined manometer. Inclined manometer, the only difference that we need to put in this case now is to consider this angle. So in this case, like what we did last time in terms of hydrostatic law, we have to put the effect of the angle. So P1 minus P2 is equal to rho G Z2. So Z2, in this case, this vertical Z2 that we have is supposed to be X sine theta. X sine theta. So which means what we are going to get here is P1 minus P2 is equal to rho G X sine theta. We know that we are going to be working with the head. So what we have is rho GH. H is the head. How did we define the head? The head, we say that is the vertical height. So which means in this case we need to look for that vertical height. So we've got this distance which is X, and we've got this angle which is theta. So to find this side, if we work with those trigonometrical ratios, so Katoa, we will know that this side we are going to get X sine theta. X sine theta for it to find the Z2. Okay. Then the rest is the same. We have to find where the pressures are equal, equate P to that P, find the pressures, and solve what we are supposed to solve for. Then when it comes to choices of the manometer, we need to look at the advantages and disadvantages of each. Okay, so you can go through this theoretical part of it to find how you can choose a manometer. So to summarize everything that we have been talking about, for us to find the pressure at 1, we need to consider these fluids differently, because fluid 1 and fluid 2 and fluid 3, they are different. They've got different densities. So to find P at 1, we need to say H3, H2 and H1. So in this case it will be P atmosphere of which you can choose to neglect atmospheric pressure since it's our datum. Or if you write it in this form, which means what you are calculating here is absolute pressure. So for us to get absolute pressure at P1 is equal to rho 1 GH1 plus rho 2 GH2 plus rho 3 GH3. Then you can find your pressure. It comes to this point, we need to find where pressures are equal. P at A is equal to P at B. Then in this case, if you want to find the pressure differences P1 and P2, we equate them in this manner. Then P1 minus P2 make them substitute formula to find rho 2 minus rho 1 GH. Okay. When you're dealing with gases, like what we talk about, we know that now the pressure due to the mercury, whatever it's inside here, is far greater. The density of the mercury is far much greater than the density of the gas. So in other words, we can just write as P2 is equal to rho GH plus the atmospheric pressure. That is if you are looking at for absolute pressure. If it's gauge pressure, we neglect atmospheric pressure as usual because it's our datum. Okay. So in conclusion, in some other industries we might not use the manometers to measure pressure. There are other devices that we can use also to measure pressure depending on what type of pressure that we want to look at. So we've got mechanical devices, Bordon tubes, strain gauge, pressure transducers, piezoelectric transducers, and all those things, which means when it comes to measuring pressure, it just depends with what type of pressure you want to find and what conditions you have here that you have to look at put into consideration. But in fluid mechanics, we'll use mainly U-tube manometers and those are the type of manometers that we have. Of course, one of the pressure gauges that we can use, the mechanical pressure gauge that you can use, is the dead weight tester. Exams usually comes to ask you draw this pressure gauge tester and how it works. This dead weight tester, how it works and the principle behind this dead weight tester. So you might need to know all the principles, the functioning of this dead weight tester to know how to use it and also to draw it. So this one can measure very high pressures, extremely high pressures, up to about 10,000 psi. So it depends on what application you want to use it for. Maybe you are dealing with those weigh station where those trucks have to be weighed or buses have to be weighed. So which means you can use a U-tube manometer there. You might need to use something that can withstand very high pressures, for example a dead weight tester. Okay, so with those few principles that we've talked about today, there are some tutorial questions that I've lined for you again that you might need to look at. So which means problem 2.11 from Pascal and also Rajput, and these questions, please try to go through them. If you've got any challenges, let me know. These questions have got also answers. So the best thing that you need to do is before you answer this question, before you look at the answer, try to answer them on your own so that you see where you are making some errors and some problems. Okay, so these are the questions that we might need to look at, and these questions, they come from Singel. I've also put some answers at the end of these slides that we have. So all these questions, they've got answers at the end. So before you look at these answers, first thing that you need to do is try to solve them on your own. Then you compare your answer with what you are going to get from these solved problems that we have. Thank you.